Okay, chapter 16, we're going to talk about acids and bases. So there's different ways to define what an acid is and what a base is. And for our purposes, the difference doesn't really matter. They end up identifying things the same way. One method is Arrhenius and the Arrhenius model. He was a Swedish scientist. He defined an acid as something that produces hydrogen ions, H+ ions in solution, and a base is defined as something that produces hydroxide ions. And this definition works really well for our level of understanding of chemistry. The Brønsted-Lowry model, which is named after Brønsted and Lowry, defines an acid as a proton donor. A proton, though, is a hydrogen ion, because a hydrogen atom has one proton in its nucleus and one electron. When you make an ion out of it, you take the electron off, what's left? Just the nucleus with one proton. So a proton and a hydrogen ion are exactly the same thing. So they define an acid as a proton donor, and a base then is a proton acceptor. So if we look at the reaction between hydrogen chloride, or as we learn to name it, hydrochloric acid, with water, what happens is that the HCl will donate this hydrogen ion to the water molecule, and we'll be left with Cl-, the chloride ion, and H3O+. And so we can say that this is an acid because it donates the proton. It donates the proton to this water molecule. The water molecule then is acting as a base because it accepts protons from the acid. So we often use HA to stand for any acid, because as we learned in nomenclature, acids start with an H. Now, if you go farther into chemistry, you'll find that there are acids that don't start with an H. But in this class, all of the acids start with H. So this could be any acid. And A, then, there is no element A. A is just the anion of that acid. So it's got a hydrogen ion and some anion A. When this reacts with water, water acts as the base, and the acid donates this hydrogen ion, the proton. So what was happening here, let's get some, is that we've got H+ moving from this molecule to that molecule. H2O, and if you add an H+, now you've got 3 hydrogens and a positive charge. This guy, if we take away an H+, we're left with A-. So this is the proton donor, or the hydrogen ion donor, and this is the acceptor. So in Mrs. K's chemistry land, hydrogen ions, or protons, are like young babies, say like a 3-month-old baby. Okay, so here is the parent holding the baby. And we're at Disneyland, and the parent wants to ride on Magic Mountain. They don't allow 3-month-old babies on Magic Mountain for obvious reasons. So what do? Do you set the baby down on the sidewalk and ride the ride? If you do, when you come back, Child Protective Services will have taken your child for good reason. No, you hand the baby to a friend of yours, the babysitter. They're going to watch the baby for you. This proton, this hydrogen ion, is too small to just be out in solution by itself. We can't have naked protons just running around. So hydrogen ions are never actually by themselves. They come with the acid, they're part of the acid. We put this in water, and some of these will be handed off to the base. The base acts as the babysitter. Okay, those words both start with B. So here we have the base holding the babysitter, and here we have the acid who has handed off the baby so they can go ride the roller coaster. Now, if we look at this is an equilibrium, which means that this reaction can go forwards, but it can also go in the reverse. Could this H3O plus ion hand that hydrogen ion back to the acid? Sure it could. That's what happens after mom gets off Magic Mountain ride, right? The babysitter hands the baby back to her. She's like, you know what, this kid's stinking and I think they're hungry, they're screaming. Here, have him back, right? Back and forth all day long. And that's what happens with acids and bases. So this is the acid, it had the baby, it handed it to the babysitter. This is the base, the acceptor. But after that happens, now we have the potential for the reverse reaction. This now can act as an acid, donating the proton, handing that hydrogen ion off to this, which can act as the base. So this is called the conjugate acid. This was the base. This is the conjugate acid, meaning related to. Do you see that these are very similar in their formulas? H2O, H3O plus. The only difference between these formulas is one has an H plus, the other doesn't. Here we have just the babysitter. Here we have the babysitter holding the baby. This is the acid. It donated the proton. Now it has become what we call a conjugate base, because after it handed off the baby, it could now be an acceptor and take a baby, right? It could accept a hydrogen ion. So this is the conjugate base. The difference in the formulas between A minus and HA is just H plus. So whether it's an acid or a base depends on whether it's holding the baby or not. The acid has the baby and hands it off to the babysitter who takes the baby for a while. So when we talk about a conjugate base, we're talking about everything that remains of the acid molecule after the proton is lost. So whatever this molecule is, you subtract an H plus, the rest of that is the conjugate base. The conjugate acid is formed when a proton is transferred to the base. This is the base, you add H plus to it, and you get that. So if we take HA and we subtract H plus from it, we get A minus. This is the acid. This is the conjugate base. I'll call him CB. Here's the base. The base accepts the hydrogen ion. We add that together, we end up with H3O plus. This is the base. Oops. This is the conjugate acid. It's just, a little bit like playing hot potato too. You hand the potato to someone and they're like, oh, this is hot, and they hand it back or they hand it to someone else. Any questions about that? Kind of a lot to absorb. So let's look at a specific reaction here. Here's our Lewis structure, our electron dot structure for water. It's got hydrogen in it. And here's HCl. This is the acid. It's got a hydrogen ion. And this is the base. Water acts as the base because it will take this hydrogen ion. So this hydrogen ion is a proton. And so just the nucleus comes. The two electrons in this bond stay behind. And that's why we end up with a negative charge. This proton goes over here and forms a bond with this lone pair. There's a lone pair of electrons there. The oxygen isn't sharing them with anyone. But now this proton needs a home, and the oxygen says, oh, yeah, I'll share my lone pair with you. Both of those electrons are actually mine, but I'll share with you anyway. And that's much better than for the proton to be out by itself. So here's the water acting as a base. Now this ion has a special name. It's called the hydronium ion, H3O+. The hydronium ion is just hydrogen holding a proton, holding the baby, holding the hydrogen ion. That's what the hydronium ion is. So what you should be able to do is identify two formulas as being conjugate acid-base pairs or not. So one of them has the baby, the other does not. So if we look at these, here the question is, which of the following represent conjugate acid-base pairs? HCl and HNO3. Are those conjugate acid-base pairs? No. We're looking for two formulas that differ only by one hydrogen ion, one H+. That's not a conjugate acid-base pair. How about this one? H3O+ and OH-. Those look a lot more similar than these two. But let's see what happens here. So OH-, if we add an H+ to that, what do we get? We get H2O. Is this H2O? No. Not a conjugate acid-base pair. Really close, but not. How about this third one? H2SO4 and SO4 2-. Do they differ by one hydrogen? No, they differ by two hydrogens. And this one I kind of showed you the long way, but look, there's 3 hydrogens on this one, and there's 1 on that one. That's a difference of 2. That's not going to work. Here the difference is also 2 hydrogens, not a conjugate acid-base pair. How about these two guys? Yeah, this is a conjugate acid-base pair. If we take that Cn- and add H+ to it, now we have one H, one C, one N, and the positive charge and the negative charge add up to 0, and we end up with this. Okay, this is the same as that, and this is the same as this. So identifying these, you're looking for a difference of 1 in the charge and a difference of 1 in the number of hydrogen atoms. Any questions? Write the conjugate base for each of the following acids. So, conjugate acids and bases differ by one hydrogen ion, but does the base have one more or one less? So, let's think about this. These are acids, right? So, let's look at the first one, H2S. When that reacts with a base, let's just use water, because we've been looking at water as a base. When this acts as an acid, what does it do? It loses a hydrogen ion, right? So we could go like this. A hydrogen ion gets transferred from the acid to the base. So what's that going to look like? If we subtract a hydrogen ion from this, instead of H2, we're going to have H, right? HS, because we've lost one hydrogen ion. And then what about this? It's got a charge on it. If we take a positive charge away, this was neutral. If we subtract 1 from 0, we get -1. So this is going to have a -1 charge. And this water molecule, when it accepts this proton, becomes that hydronium ion. If this is the acid, which one of these is the conjugate base? The HS or the H3O? The HS, right? This is the acid. Let's maybe write that in here in a different color. This is the acid, and this is the base. So the acid becomes the conjugate base, and the base becomes the conjugate acid. So to find the conjugate base of these acids, what we need to do is say, okay, the acid is the parent holding the baby. They become a conjugate base after they've passed the baby off to someone else. So we need to subtract an H plus from each of these. So we already did this first one, and we get HS minus. Right, that's what we came up with right here. How about this one? Oops, this one. HS minus. Subtract an H plus. What do we get? S2 minus. Sometimes we show these with a slash because they're a pair. What happens if we take a hydrogen ion, H plus, from NH3? NH2 minus. See, this one had a negative charge. We subtract 1 because we're taking away a charge. We get -2. This one had a 0 charge. We took a charge away, so we get -1. This one had 3 hydrogens. We're removing 1. We get H2. How about H2SO4? Subtract 1 hydrogen. What do we have? HSO4. The charge was 0. Subtract 1, we get -1. So it's really good to understand, the previous stuff that I talked to you about and showed you the equations. But honestly, doing something like this is something that I could probably teach my 5th grader how to do. Now, the trick is expending the effort and being willing to remember what to do. Okay? It's not that it's hard. We're subtracting an H and we're subtracting 1 charge. It's remembering. Okay? Let's do another one. Write the conjugate acid. So at the beginning we have an acid and a base. Right? The acid is holding the baby and hands it off to the babysitter. The acid becomes the conjugate base. The base becomes the conjugate acid. The base was the babysitter who accepted the baby. So now to write the conjugate acid, we need to add a hydrogen ion. Ooh, acid and add both start with A. To find the conjugate acid, you're going to add. I like that. I don't know why I never thought of that before. So this is add a hydrogen ion. Always helps to have little gimmicks like that to help us remember what we're supposed to do. So if we take PO4, 3 minus, and add a hydrogen ion, how many hydrogens does it have right now? 0. So now it's going to have 1, right? So we always put the H's on the front. So there's the H, copy down the rest of it, PO4. Now the charge was 3 minus. If we add a positive to that, we get 2 minus. There we go. IO3 minus. This is the base, the conjugate acid. We add a hydrogen ion. There's no hydrogen ions. There's no hydrogens in there right now. Put a hydrogen on the front. Copy the rest of the letters. Then look at the charge. Minus. -1. Add 1 and we get 0. We don't have to write a 0. So there we go. NO3 minus. What's the conjugate acid? HNO3. We're adding a hydrogen and a charge, +1. This was -1, adding +1 gives us 0, which we don't write. What? NH2 minus. NH3. It had 2 hydrogens. We're going to up that to 3. The charge was -1. We add 1, we get 0. HNH2, while that's not the normal way we would write it, I would look at that and say, yeah, it means basically the same thing, because all the other ones were putting the H on the front, right? And this one we don't, but I don't really expect you to know that. But I give you multiple choice exams, right? NH3 is the correct way. This is the correct way. So if you were doing this on an exam, and then maybe there were choices like NH2 minus and NH3 and NH2 and I don't know, NH4 plus. So maybe those are the multiple choices, right? And you looked at this and you came up with HNH2. Which of these is the most similar to HNH2? The NH3, right? Because this has the same number of hydrogens and nitrogens. This one is kind of similar, but it left off the H on the front. That's kind of important. That's more important than how the letters are arranged, that we have the correct number of each letter. Okay? Any questions?